So I'm co-founder CTO of Griffin Bank. We're a fully authorized UK bank as of February 29th of this year. We are B2B, so our customers are both regulated and unregulated fintechs and software companies with complex payments. We're also API first, so we have API to onboard a bank, or API to onboard a customer, API to create a bank account, API to make a payment. And so now I have lots of opinions on software testing and correctness, and you can hear about them. We also built our own core banking system. So every time the subject of testing comes up, you get things like, oh, you should have a lot of unit tests, and you should have some integration tests. And like, wait, what is the actual size of a unit test? Like, how do I know if this is too big or too small or whatever? And the other thing that comes up is you get these like, oh, you should have 70% unit tests and 30% integration tests. And, oh, my tests are too slow and my tests are too flaky. And these problems are all related. And a lot of people talk past each other about, oh, you need more end-to-end tests so you get more coverage. And no, you need more unit tests so they're faster and more reliable. And they're talking past each other because there's actually another axis here, which is pure versus impure. Tests are slow and flaky because they're impure. They have side effects. They're non-deterministic. Unit tests are typically faster and more reliable because they're pure. And so people arguing like, oh, you need more unit tests. What they're saying is you should go to this upper left quadrant. And what they actually should be saying is you just need to move to the left. You need to remove non-determinism. So when people complain about, oh, my tests are too slow and flaky and they take too long, you actually don't have a testing problem. You have an organization problem. And every good Clojure talk requires a trip to the dictionary. So today we're talking about organ and organize. So organ is a noun, comes from Latin organum, means a part of a particular, forms a particular job. And then it means both body organ and like musical instruments in general, and then like the organ in particular. So then from organ, you get organize, which is like the process of creating organs. And then once you create organs, you say like, I'm responsible for this and you're responsible for that. And I give you this and you give me that, right? So you have clear boundaries, you have clear separation, you have responsibilities. So your code is hard to test because it's not organized. And, I'm sure you say, oh, but my functions are well named and I don't have too many functions in my source files and my source is organized. Yes, I believe that. Your system is probably not. And that just because your functions are well named doesn't mean the system has clearly defined responsibilities. So we look at an example of this at the small scale. So on the left we have a C function, takes two ints, returns an int, and on the right we have the Haskell version, same thing. So what is the C version promising you? Well, it takes two ints and returns an int. What is it promising not to do? You have no idea. Is this thing reading or writing to the disk? Is it, dropping your database? Is it sending network messages? Is it spawning threads? Is it segfaulting your process? No guarantees at all. And on the right, if the Haskell version isn't calling unsafe perform IO, you get a lot of guarantees here. It's pure. It's thread safe. It's cacheable. It's memory safe. This isn't an argument about Haskell versus C or static typing or anything, but like if you take any piece of code that you rely on, functions, libraries, third-party services, anything, they offer a set of guarantees, and you can order your set of guarantees, from less to more, or from fewer to more, and from weaker to stronger. And in general, the stronger the guarantees and the more guarantees you're getting, the more valuable that service or that code is to you. And you can rely on it more and then build stronger things on top of that. So, and this isn't just at the function level. Like this scales up to the system level. And there are actually a lot of the guarantees that you really care about from the system level are very hard to test, especially, using functions. So things like, does the service deliver messages in order? Is it resilient to hardware failure? Is it race free? Is it idempotent? what is its P99 latency less than 200 milliseconds? Those kinds of things. And those are very hard to establish at the function level, but you still need to have them to have correct systems. And if you need to have them, then you need to test them. So testing pure code is mostly a solved problem now. The answer is called quick check. It was written by a guy named John Hughes, who started in Erlang and then ported it to Haskell, and now it's been ported to every major language. It's good. You should use it. So on the left, you have the standard example-based test, where you say, okay, I have 2 inputs and I have 1 output, and 1 + 2 = 3. Great. Quick check separates those into 2 separate problems. One is generating new inputs, and then the other is verifying that those inputs produce good outputs. And this is already really powerful, because on the left, you have to think of like, oh, I'm going to do, this set of input cases, like you have a fixed set. Whereas like addition, the function says, I take any 2 integers. Well, you've only tested 2 of them out of, 2 to the 64 times 2 to the 64. So with quick check says, I'm going to take any 2 integers, and it uses a random number generator to produce any set of legal inputs. And then separately, you have a property where you say, for any 2, by the way, this isn't a complete specification of addition. It turns out you can't hit that on a slide. But it is a simple property that is useful that you can fit on a slide. And so you say, for any 2 positive integers or non-negative integers, you get a larger integer. So this forces you to think in terms of invariance, which is very useful. You say things that are always true. So I want it to be always true that if I accept a user's request, I won't forget it. I won't drop it on the floor. But you can't test that. You can't validate that using individual examples. You need to say, over millions of cases, I've never observed this thing happening. So therefore I have confidence that it's not going to happen. So quick check is great. You should use it, but it has a few requirements. One is that we're hooking this up to a random number generator, so we need to generate a large number of test cases. And then if we're generating a large number of test cases, we want them to run quickly, right? So then you need your test to be fast. And the other thing is you need your test to be deterministic, because if we're generating, one of the things QuickCheck does is a process called shrinking, where you say, I'm going to generate 1 million test cases, and then I found 1 failure, and now I want to shrink that to the smallest, simplest to understand test case, because it turns out if you generate, thousands of messages, and then you say, oh, this 50 message sequence caused an error. Like, okay, great. What was the actual problem there? So then QuickCheck will try to shrink that, and it can frequently get down to like, oh, message A, message B, message C causes the failure. So that's incredibly powerful and useful as a developer experience. But to do that, you need reproducibility, because if you get, if you're running this thing thousands of times and you get a flake 1% of the time, and then you run it again, how do you know that you fix the bug? So to fix it, you want to be able to say, run that same sequence of inputs again and know that if it passed, it was correct, and if it failed, the bug is still there. If you have non-determinism, you can't prove that. So reproducing test failures requires determinism. So there's this great talk that's got testing deterministic simulation, testing distributed systems with deterministic simulation. So this guy, Will Wilson, was on the Foundation DB team. And Foundation is one of the 2 most correct databases on the planet, the other being SQLite. And so when they started to build this, it was kind of an unsolved so Foundation is a distributed database that runs at web scale, and it's strict serializable. And it was kind of an unsolved problem of whether or not you could even build a distributed database that was both fast and correct at the same time. And so when they started, they knew that fast databases already existed. It's like Mongo is already there. If you're happy with Mongo, you can go use Mongo. But they wanted it to be correct as well. So what they did was they isolated every source of non-determinism behind an interface. So that's, reading and writing to disk. That's sending network messages. That's the system clock. And the really fun one is thread scheduling. So they wrote their own C++ dialect, then added actor-style concurrency to it. And then the entire system is a collection of these single-threaded actors passing messages. And in production, it runs on multiple machines. But when they're testing it, you can run the entire cluster in a single actual process, and then you can simulate the entire cluster in a single process. And then using, then they can say, okay, if this actor sends this message, and then actor B wakes up and processes the message, and then C wakes up and processes the message, it works. But then what if we do all possible interleavings of thread wake-ups and prove that you never see uniform results? And you run that millions of times, now you know that you don't have races. And this is incredibly powerful. And this is probably the only practical way to get confidence that you have these system level properties of, I'm resilient to the failure disk, I'm resilient to race conditions, things like that. So the lesson to this: write your own dialect of C++, isolate all sources of non-determinism and put them behind interfaces or protocols, whatever you call it in your language, and hook it up to QuickCheck. So for the mortals who don't want to write their own C++ dialect, or you don't have a greenfield project, what do? You incrementally approach this. So there's this great blog post by Newbank a couple of years ago. It was called How They Killed Their End-to-End Test Suite. And it was a great blog post, and it really inspired me, but unfortunately they didn't provide source code. So I did. So this is called test.contract. It's basically a quick check for testing stateful systems. And it follows the lessons of FoundationDB. So traditionally, if you want to test a third-party API, you want to test your code against like a database or a third-party API or whatever. You have a couple options. One of them is just run it live. I'm testing against a third-party service, so I'm going to send actual requests to it. But you want to do quick check. You want to get lots of coverage. Maybe you're not allowed to send 1,000 requests a second to this thing. Maybe it doesn't support it. Maybe you're running tests on the train or on the plane or whatever. But it's also slow and non-deterministic. So so your other option is mocks. You get out a testing library and say, okay, the first time I call foo, return 1. The second time I call it, return 2. What happens if I call it the third time? What happens if I call foo and then bar and then foo? What happens if I call it from multiple threads? The other big problem is these can hallucinate. So how many people here have used mocks, got their test screen, deployed it to production, and then things immediately broke because the mock didn't correspond to reality, right? Like, I've done that multiple times. So we wanted to fix both of those. So it's step one, define an interface or protocol or whatever it is you call it. S3 is the first one that we used, the first one that we replaced with a contract. And so you define your protocol, and then you attach generators and specs to it, and it worked. That gets you enough to write a few unit tests, but very quickly you realize you need state, because what is the return value of get object? Okay, well, it could return the object or it could return 404, right? And it could return either of them randomly because QuickCheck does everything using random number generators. But very quickly you realize, okay, if I call put and then get, I definitely want it to be there in my tests. So you very quickly need to model state. So we define the model. So this is pure closure code that describes the behavior of S3. And I know this is dense. I'm not expecting you to read it all. But so we say, for each collected protocol methods, define a generator for the arguments, and then define the behavior of this method. So in the current state, if I'm called with these arguments, I'm going to return some stuff. And so the spec for the expected return value is this, and then the generator for new return values is this. And then, optionally update the state. And it turns out this is actually pretty good. Like, you don't need to completely replicate all of S3 to get useful results out of this. The detail of your model will depend on the detail of your tests, which will depend on the amount of the actual API that you use. So then once you have a model, you can do a lot of cool things with it. So you can generate a sequence of arguments, you can get the expected return values, and then you can call them against the real thing. And then once you've done that, you can say 1,000 times I called S3 and I predicted it was going to return this, and the return value always matched my predictions. So that gives me confidence. And now that's completely isolated from the rest of your code, because you have your S3 model stuff over here, and then you can generate a mock from that model and then use that in all of your other tests. So now you've completely removed a source of non-determinism in your test suite. So we have 8 or 12 of these now, with like four AWS APIs, and the rest are other third-party services. Right, so you can verify your model, you can use the mock for your tests. Then the other unexpected benefit was that you can use this for local development. Like, how many people here you have to work against a third-party service that's only available in staging and production, right? Like, that really sucks. So this way you can very easily set up a reliable system on your laptop and know that it will behave like production. The next thing you can do is build a test proxy. So this is, we have the model, we have the real S3, and you can run code against both of them at the same time and compare results as they come back. This is really useful in like staging, because you want extra confidence that, okay, maybe my tests aren't exercising everything that production is actually doing. GitHub had a great article a couple of years ago about how they wanted to rewrite their authorization service, but they wanted to rewrite it because it was gnarly, but then it also means it's hard to know that you've caught all the cases. So what they did was they ran both versions side by side in production, and the old one was still authoritative, and then every time the old and the new service disagreed on what, should this user be allowed to access this resource, they logged an error, and then go investigate the error, go deploy a fix, and then once it ran for 2 weeks in production with no errors, they had confidence that the new version could be safely switched over, and they could turn off the old one. So you could do that, like in staging, for example, or load tests. Probably don't need to do it in production. And then the final thing that's really cool is you can inject errors. So we have our model of S3, and then you say, I want to verify that we are resilient to transient network errors. How do you do that? Well, you can wrap your function and say 100% of the time return an error. Okay, so everybody's system has this big mess. The great thing about this is you can replace every line with a contract, and then you can test your services in isolation and have confidence that everything is working. And one of the reasons this is called a contract is that it binds both sides. So you can say, is the API always producing valid values? And then downstream of the API, are the consumers handling all possible valid inputs? Right. And then you can say, oh, but I don't know what the contract on my database is. Like, well, yeah, that's a problem, right? If you don't understand what the thing is guaranteeing, like how are you expecting to build a correct system on top of it? There's this guy, Kyle Kingsbury, who's been breaking distributed databases for a decade, and he has this helpful chart where basically the one on the top is correct, and then everything else is like a different word for bug. And it turns out it's actually easier to write a contract for the correct version, and because all the other ones are like, oh, sometimes when you read a value, it might rewind in time, or sometimes it's not thread safe, or you read a value from one reader and another reader will have different views. And it turns out that's really annoying to specify. So if you just have a very simple contract and use a very correct system, it's much easier to understand what's going on, and it's much easier to know that you have built good software. So summary, isolate all side effects, non-determinism, put them behind interfaces. be explicit about the guarantees, both the guarantees that you're providing and the guarantees that you're consuming, and then test them. Because, like, as Kyle pointed out, a lot of vendors they're saying, oh, we're resilient to the failure of hardware nodes. And it's like, well, actually, no. Like, in the most basic test, we just turned off hardware nodes and saw data loss. So, thanks. We're hiring.